Okay, this is lecture 2 of the Nack Network for Nanotechnology Workforce Education on Materials Overview for Nanotechnology. This part 2, lecture 2, is going to be on ways of classifying materials by bonding types. So one way to classify materials is by bonding, and that's what holds the materials together. What is bonding? It's the interaction among valence electrons that holds atoms together in molecules and in materials. So if you missed the valence electron information, go back to lecture 1 and it talks about valence electrons. Why does bonding occur? It occurs to reduce the stored energy. So you'll learn in physics that everything wants to go down to the lowest energy. It's just how nature works. The lower the energy, the better, right? So that's what they naturally want to do. So that's the basic reason why bonding occurs. How does it occur? Well, between atoms. So when you're making a molecule, you have bonding between atoms, and there are 3 main bonding types, and that's ionic, covalent, and metallic. Ionic bonds are when the valence electrons are transferred from one atom to another. Covalent bonds are when the valence electrons are shared between the atoms. And in metallic bonds, the valence electrons are essentially free and shared equally among all the atoms. And that's why for metallic materials, you can have electricity run through it because the electrons are free and they're able to run through the wire to create electricity. Okay, so those are between specific atoms, and they're the strongest types of bonds kind of in general. Then we have what in Regents chemistry we call attractions, and these are between molecules. So they're not bonds. Bonds are actual chemical bonds. These are actually attractions. Some can be quite strong, but they're not as strong as chemical bonds. So one type is called hydrogen bonds. Again, that's a misnomer. It's really hydrogen attractions. And it's an attraction between the partial positive and negative sides of a molecule. And in specific for this particular kind of attraction, it's between a hydrogen atom on one molecule and a nitrogen, oxygen, or fluorine atom on another molecule. And those two things are attracting each other. And I'll talk to you a little bit more about that. So the hydrogen would be a partial positive, nitrogen, oxygen, or fluorine would have a partial negative charge. And, as you guys know, opposites attract, so plus is attracted to a negative. Van der Waals forces or van der Waals attractions are attractive or repulsive forces between molecules or between parts of the same molecule arising from electric force variations. So frankly, we have those clouds of electrons. They're not static. They're not necessarily uniform. One moment there might be more electrons on one side of an atom versus the other, and therefore it would give that side a little bit of a negative charge. Then the next, split second, it might move. So those charge densities are constantly moving, and that gives van der Waals attractions, I'll call them. I should have changed the slide. How can we begin to understand what type of bonding can occur for a different set of atoms? A good place to start is to look at the electronegativity of the atoms involved. Electronegativity is defined as the degree to which an atom attracts electrons. So if I have a high electronegativity, I'm really going to attract electrons to me. If I have a low electronegativity, I can't really take any electrons from somebody else. I'm too weak. So here's a periodic table, and I liked this thing here. What it shows is that as the atomic radius decreases, going from left to right in a row, or we call them periods, as the atomic radius decreases, the ionization energy, which Mr. Musio in chemistry talked about, increases, and electronegativity increases. So electronegativity, we just said, is how strongly can an atom attract the electrons from another atom to it. So on the left-hand side, it's low electronegativity. So this guy can't really attract atoms. This whole column can't attract atoms to it. but this column, column 17, will attract atoms to it. Now, we're going to forget about column 18 for a moment and just go up to column 17. So electronegativity increases as you go from left to right, with the exception of column 18. All right, I was intrigued with this slide, electronegativity differences. So xenon difluoride, so this is xenon difluoride, di means two fluorine. Xenon difluoride has a chemical formula of XeF2 and is one of the most stable xenon compounds. It is useful in micro and nano fabrication, where it is used in the gas phase for selective removal of materials such as silicon, molybdenum, tungsten, titanium, zirconium, hafnium, vanadium, tantalum, niobium, boron, phosphorus, germanium, arsenic, and mixtures thereof, from silicon dioxide, silicon nitride, nickel, aluminum, titanium, nickel alloy, photoresist, phosphosilicate glass, boron, phosphosilicate glass, polyimides, gold, copper, platinum, chromium, aluminum oxide, silicon carbide, and mixtures thereof. So just a bunch of things. But the reason I thought this was especially interesting is I'm pretty sure when I was in chemistry a long time ago, basically they said that the noble gases, which xenon is one of the noble gases, it's in group 18, really doesn't react. So, and it's true, they don't react unless you have very specific and high energy, I would say, conditions to make it react. So I was really intrigued seeing this noble gas compound that they were talking about here that's used in a lot of nanotechnologies. All right, anyways, so types of bonds, let's get more into it. Ionic bonds, we talked about them transferring the valence electrons. So ionic bonds have large electronegativity differences, meaning that one atom has a very high electronegativity and the other atom that it's bonded to has a low electronegativity. So if you subtract, there's a number for electronegativities. If you subtract those two numbers, it's larger. Ionic bonds are created when an ion is formed when an atom gains or loses one or more electrons, right? So you have a positive atom when it loses its electrons to the other atom, which has a negative charge. So positives and negatives attract. Ions with opposite charges are attracted to each other. Ionic bonding involves the transfer of one or more electrons between atoms. We said that. Atoms that lost the electron is called a cation. Atoms that gained the electron is called the anion. This is stuff we went over in chemistry recently, so that should be very familiar to you, but not the bonding of it. We're going to get into that very shortly. So positives, opposites attract, right? So positives and negatives attract. You guys know, or seniors know, that sodium, which has one valence electron, tends to lose that, right? It's easier to get rid of one than gain 7. So you could have the octet in the outer orbital. So it's easier to lose one. When it loses the one electron, it'll have a positive charge. Chlorine, on the other hand, chlorine has 7 valence electrons in the outermost shell. And when it gains 1 from sodium, it has 8. And then it'll have a -1 charge, right? So I should say for the 10th graders that you might have learned this in before, but the atoms generally try to get to an octet, 8 valence electrons. That's kind of what almost all atoms want, 8 valence electrons. So for sodium that has only 1 in the outermost shell, it's easier to get rid of that 1. Whereas chlorine, which has 7, it's easier just to gain an extra 1. So when sodium loses the 1, the next outermost shell here has 8 valence electrons, so that's good to go. And then when chlorine gains that 1 extra electron, chlorine has 8 electrons in the outermost shell, and chlorine is good to go. All right, so because if you looked up the electronegativities, you'll see chlorine has a very high electronegativity, sodium has a low. The difference is pretty high, so that means that the chlorine could just take the electron from the sodium. Electron is transferred to the chlorine, and bonding in ionic solids is an electrostatic attraction. So opposites attract, positives are attracted to negatives. So that's ionic bonding. Covalent bonding, whoops, this circle is in the wrong spot, sorry. Covalent bonding is when the electrons are shared between atoms to attain the octet and become stable. This occurs between atoms of similar electronegativity because neither atom is strong enough to actually take the electron from the other. They're kind of about the same similar type of strength. So they kind of have to share it, right? Because neither of the atoms can take it from the other. The degree of electronegativity difference makes a bond polar. So if they're less similar in electronegativity, you might have a polar bond. If they're very close in electronegativity, you would have a nonpolar bond. And covalent bonds are the strongest of the chemical bonds, and it's very directional. So here's an example. Here I have chlorine with 7 valence electrons and another chlorine atom with 7 valence electrons. And so this circle is supposed to be, you know what, I'll annotate it right here because I messed that up. But this circle is supposed to be right around here. So, so here's the 7 from the first chlorine, the 7 from the second chlorine. If they share their 7 electrons, they both share it between each other, then each chlorine atom now has 8 electrons, right? So this chlorine atom sees 2, 4, 6, 8 electrons, right? This chlorine atom here sees 8 electrons, which that was a terrible circle. I want a different color. One sees 8 electrons, right? 8 electrons, 2, 4, 6, 8. And if I look at what this chlorine atom sees, also 8 electrons, 2, 4, 6, 8. And you know, 8 electrons, 8 valence electrons is the lowest energy thing. So it most every atom wants 8 electrons. So this would actually be a non-polar bond because the electronegativity of chlorine is equal to the electronegativity of chlorine. So this is the difference of those two is 0. It's a non-polar covalent bond. All right, so that's that. Let me go on to the next one. All right, I have to clear my stupid annotations. Clear. Oops. All right, so properties of covalent bonds. Let's do this. Clear all drawings. The sharing of pairs of electrons between 2 atoms, covalent bonds are directional. And what does that mean? They hold a specific angle relative to each other. And I'm not going to get into why, but look at for H2O, this thing has kind of a bent, it's kind of bent. The 2 H's are not right across from each other. But for xenon difluoride, the 2 fluorines are indeed right across from each other. So they have different shapes. H2O is always going to be in this kind of angled shape, and xenon difluoride is always going to be in this straight shape. And you can also, for covalent bonds, have multiple bonds between 2 atoms, which I won't really go into. All right, here's an example of covalent bonding in DNA. So each of you guys remember what a DNA is, right? So it has a sugar and a phosphate backbone with the bases going across, right? And so all of these atoms are covalently bonded, but when the bases are hooked together in the middle, that is a hydrogen bond attraction. So if you look really carefully at this, the base pairs in the middle aren't actually connected together because they're attracted with hydrogen bond attractions. Anyway, I thought that was cool, so I left that in there. Here's an example of a silicone crystal structure bonding. It's covalent bonding because they're all silicon atoms, and we'll go into that more in a different project, I think. So electronegativity and polarity. This is very wordy, and I apologize. Molecular polarity is dependent on the difference in electronegativity between atoms in a compound and the symmetry the asymmetry of the compound structure, right? So is it symmetrical or not symmetrical? That's the key here. For example, a molecule of water is polar because of the unequal sharing of its electrons between the oxygen and hydrogen, in which the former has a larger electronegativity than the latter. So ultimately, what this whole thing is saying is, look at the shape of this water molecule. I have more electrons here on the bottom than at the top. So the electron density is different from the top and the bottom. The molecule is not symmetric. You know what symmetric means? It looks the same if you cut it in half on both sides, like, right? Like a mirror image. If I cut this water molecule in half up and down wise, yeah, it looks the same. But if I cut it in half sideways wise, the top does not look the same as the bottom. So it's not symmetrical. Therefore, this is a polar molecule. This nitrogen molecule, right, has two nitrogen atoms stuck together. This is symmetric. If I cut it in half this way, it looks exactly the same. If I cut it in half up and downwise, it looks exactly the same. So this is symmetric and it's going to be polar. This is not symmetric and it's symmetric is nonpolar. Sorry, I misspoke. And this is not symmetric, so it's polar. So polarity underlies a number of physical properties, including surface tension, solubility, melting, and boiling points. So if a molecule is polar or nonpolar, it really affects all these kinds of properties. Okay, this is a cool slide. I like this. So metallic bonding is formed when you just have pure metals together. And electrons are fully shared and are essentially free. So here is a picture of a magnesium metal. And you have these core atoms here, the core part of the atom, right? But they all have a 2+ on there because the 2 electrons that are in the valence shell or the outer valence shell of each of these atoms are free to move around all over the place. The overall charge of this metal is 0, it's neutral, but they don't show the sea of delocalized electrons just moving all over the place here. They're there, they're not showing it, but they're there. So it's overall neutral, but the 2 delocalized electrons for each atom are just running around wherever they want. To get more into the hydrogen bonding attraction, I'm going to say that it's an attraction, not a chemical bond. It's a form of association between an electronegative atom that wants electrons and a hydrogen atom attached to a second relatively electronegative atom. So water is that case, right? So what happens is that this water molecule, the hydrogen has a little bit of a positive charge. The oxygen has a little bit of a negative charge, not full negative, but partial negative. So this partial positive is attracted to the partial negative on the next water molecule, and so on and so forth. So this is a hydrogen bond attraction. It's the strongest of the attractive forces between molecules, and it's responsible for the high boiling point of water compared to other molecules of the similar size and molecular weight. It's a very important bond in biology. We already talked about the DNA strands being attached with hydrogen bonding, between the bases, as well as molecular recognition and self-assembly systems. Here's some examples of an acid and water, carboxylic acids and water, how they're kind of using hydrogen bonding and DNA base pairs, which is why I want to show this. This actually shows it, right? All right, last and the weakest attraction between molecules. So when I say attraction, I'm talking between molecules. And when I say bonds, I'm talking between atoms, right? So we had hydrogen bonds, which is an attraction. Van der Waals is an attraction. So it acts between atoms or molecules that are not bonded to each other and includes several types of interactions, which is dipole-dipole. I usually separate dipole-dipole out as a separate type of attraction, but this one uses it under the van der Waals interesting. Dipole-induced dipole and dispersive forces related to the cloud shift, which is what I was talking about before, of electrons of atoms or molecules. So this is where the cloud, the negative, partial negative cloud around a molecule like moves around constantly. All materials are subject to these relatively weak short-ranged forces, but these types of forces are the dominant type of interaction between nonpolar organic molecules. And even though van der Waals forces are weak and short range, they can be very important at the nanoscale because distances between things can be very small. So that's really why they're so important in this context. For example, van der Waals attractions are responsible for surface tension and capillary action. So, you know, you have water, or even if you took a paper towel and put one end into a cup of water, the water's going to like soak up into the paper towel. That's from capillary action. And it's really van der Waals attractions responsible for that surface tension there. Why is this important for nanotechnology? There are a lot of nanoscale devices and how would I call it? Processes that use this capillary action and surface tension. Well, I think more capillary action as part of their function. So it's kind of important. They're using van der Waals attractions affecting nanostructures. I think building this nanostructure, they're using the capillary attraction. So super important, especially at the nanoscale. And I think that ends the bonding portion of this slide deck.